Welcome back. So let's look at the model then. It's the easiest to contrast it with cloud storage services. So the key value model, that's what you see on the left, that's what we did last week. The idea that you can identify every object with a key, and that key is, in the case of S3, the bucket ID plus the object ID. Together, they are the key. In the case of Azure, that would be the account ID, the container ID, and the object ID. Okay, but in the case of a distributed file system, and usually this is what is implied with file system, we have a hierarchy of directories and files. So the hierarchies of directories and files, you should be familiar with it. This is what you have on your laptops and desktop computers, right? It's recursive. You can have directories in directories in directories, and then at the end you have the files, and this is where it ends. The files are the leaves of the tree. All right, this is called the file hierarchy. Note the difference in terminology, that on the left, we use the word object for the key value model. We call the values an object. In the case of a file hierarchy, we use the word file instead of object, but it's really the same thing. In the end, a file or object is the same thing. This is, in the end, what your data set is stored at. So here we say object, and for this, and this, we say file. Okay? So this is a file hierarchy. It's not flat anymore. We do have a recursive structure of directories or folders, depending. I think it was across Mac and Windows, and over the years, in some years they call them directories. In some other versions, they call them folders. But this is only a matter of terminology. Okay, so that's difference number one. And then there's difference number two. Difference number two is that in the case of object storage, the object is a single big monolithic chunk. That's the object, up to 5 terabytes. In the case, however, of a distributed file system, we do divide the files into blocks, right? So in that case, we have 8 blocks, 1, 2, 3, 4, 5, 6, 7, 8. And they are exposed to the user through the API of the file system. So you can actually see the blocks. There is block 1, there is block 2, and so on. They are exposed to you, right? So this is called block storage, as opposed to object storage. Now you might tell me, okay, yes, but when you showed us at the beginning of this lecture today, Azure Blob Storage, there was already the blocks in there. Yes, that's true. And in fact, Azure Blob Storage is already already doing distributed file systems in that sense, because they use blocks. But in S3, there is no such thing as a blocks. And do not confuse a block and a part. When I told you that in the API of S3, you have a way to upload it into several parts, this has nothing to do with blocks. The parts are specific to the way you upload it, but once you're done uploading, it disappears. There are no parts anymore, just a single big objects. But the blocks are really part in the distributed file system of the API. So again, difference number one, now we have a hierarchy of directories and files. Difference number two, we expose blocks to the user of HDFS. That's called block storage. Now, words of, I wouldn't say warning, it's just real life. I said block. If you look at the original Google File System paper, GFS, they don't call it a block. They call it a chunk. We will see when we talk about MapReduce that they will use the word split. When I told you about storing data sets in S3 and splitting your data set into multiple objects, I use the word shard. Mathematicians will call it a partition, and so on and so on. So there are many, many different words you can use to actually mean the same thing, right? All you're doing is dividing something large into several smaller things. And you can call these smaller things a block, a chunk, a split, a shard, a partition. It doesn't really matter, right? This is really the idea. Now, if you manage to remember that in the context of HDFS, we say block, GFS, we say chunk, MapReduce, we say split, and so on, that's good. But I want you to focus on the idea of that, the fact that we really divide something large into several smaller things that we call blocks. Okay, So now a summary in a single slide of the model of HDFS looks like this. We have this hierarchy of directories and files, and every file corresponds to a list of blocks. Right? List because there's an order. The order of the blocks is important. Okay. Only the files, by the way, the directories, they have no blocks. The directories are only here in order to give the hierarchical structure to the file system. For whom is that clear? Right? This is the model, it's all in there. This is the model of HDFS, that's it. Now, why blocks? There is a first obvious reason. Is that if you have a file that is 1 petabyte large, that surely won't fit over a single machine. Today, in 2024, we do not know how to build a hard drive that has a 1 petabyte of data. Technologically, we cannot do it. Maybe in 10 years or in 20 years we can, but today we cannot, right? So if you want to store a file that doesn't fit in a disk, you anyway have no other way than to split it into smaller chunks or blocks or shards or partitions. So this is the first reason. The second reason is that it's actually a great level of abstraction to have these blocks, because when we actually will start looking into MapReduce and Spark and into how to process all of these files, this will allow us to do things in parallel, right? If you have a single object like this, it's not so obvious to do anything in parallel on that. There's only one object. But if you have blocks, that's easier, because then you can do things on the blocks in parallel, right, on different machines. So this is kind of the intuition why we actually like blocks, right? Another reason for blocks is that it's kind of liquid. What do I mean with liquid? I mean that if you consider on the logical level all of the blocks of the entire HDFS file system, maybe you have millions or billions of blocks that would be on the left, you have to spread them over thousands of machines. So if you have, I would say, a few billion blocks, it's easy to spread them over 1,000 different machines. You just imagine that you have, this is a big bucket full of small blocks. You could almost take it and pour one by one into the buckets, just as you would do with water. So this is the idea. It's liquid in this way. But that doesn't work. That only works, if we find the right size for the blocks. Because imagine that you take enormous blocks. A block, imagine we take 5 terabyte blocks. It's going to be different from taking 1 kilobyte blocks, for example. The size of the blocks would change. So this is why I have this question for you. The blocks, they already exist on your laptops. You might not know it, but your laptops here also store your files in blocks. These blocks on your machine, they are roughly 4 kilobytes. That means that whenever your computer reads something from disk or writes something to disk, it's always doing that 4,000 bytes at a time, 4 kilobytes at a time. The same goes for a relational database, even though in that case, we might go all the way to 32 kilobytes, but this is the order of magnitude. So my question to you, I'll have a quicker question for that. How big do you think the blocks in a distributed file system should be, keeping in mind the constraint I told you about? We want to be throughput bounded, right? We don't want to be latency bounded, we want to be throughput bounded. Now I'm going to ask you the question and see what you think, how large these blocks should be. Here you go. I have to pick the question again. The one, yes. So what is an ideal size for a block in a distributed file system like HDFS? And I try to lure you into each answer with a good reason. So first, 32 kilobytes, like on a local file system. It's the order of magnitude that is important, right? Like, for example, in a relational database system like PostgreSQL. Or 128 megabytes, good compromise between latency and throughput, right? Because I told you that this is what we care about. Or maybe 2 terabytes, because that fits on a local disk, and that's the optimal way of using a single machine, right? Or maybe 512 petabytes, because that's big data. So we need these huge blocks for the whole thing to work. So what do you think? 32 kilobytes, 128 megabytes, 2 terabytes, 512 petabytes. All right. Somehow I sense that we will have a majority in here, and that the majority is correct. Congratulations. Indeed, 128 megabytes. I will explain, give you an intuition of that. You share. And normally, if I prepared correctly, this is where we get exactly where we were. There you go. So the first thing is that you notice these blocks here, 128 megabytes, this is much larger than the blocks we have on a local file system, right? That's a huge order of magnitude. So I'm going to reason by taking it to the exaggeration on both sides and try to make you imagine what would happen. First, imagine that you have blocks of 2 terabytes. Imagine. So it means that on each machine, maybe you're going to have 1, 2, 3, or 4 blocks, right? And then you have 1,000 machines. Now imagine using that system. You have to upload file to that system. You have to actually process the files. First, imagine the usability of uploading to a system where the blocks are 2 terabytes. This is what we discussed earlier today. You're going to get network errors the whole time. You're going to have to try several times whenever you try to upload anything in there. So first, it's not going to be very practical, these 2 terabytes. The other aspect is that 2 terabytes is not very liquid. When you want to spread the data over the cluster, it's kind of too large to actually be liquid. And this is an intuition that we will come back when we actually look at MapReduce. We will understand why it is important that on each machine, we don't have just 1, 2, 3 blocks, but we have thousands of blocks on each machine to have some liquidity. So 2 terabytes is way too large, right? That would definitely be throughput driven, but not very practical to use. For whom does that make sense? All right, so 2 terabytes too large. Who understands that 500 petabytes, that's definitely a no-go? Right, that doesn't even fit on a machine, 500 petabytes. So this one is a no-go. But now I have to explain to you why we don't use these smaller blocks. Why after all, don't we use 4 kilobyte blocks? Then the model you should have if we had blocks that small is that you wouldn't have a few thousand blocks on each machine. You would have millions of blocks, tens of millions of blocks on each machine. So imagine a cluster with 1,000 machines, and on each machine, there are tens of millions of blocks. Now, what I would like you to imagine is that system now functioning. Like you query data in there and you process blocks, knowing that every time you touch a block, there is some latency. And now imagine that you have to analyze the data set, and that data set is a petabyte of data, but it's split into kilobyte blocks. Now, I'm going to try to get it right. How many blocks does it have if you have a petabyte data set and the blocks are in the kilobyte range? So kilo, mega, giga, tera, peta, you are at 1 trillion. So you're looking at 1 trillion blocks for a petabyte data set. And imagine that each one of these trillion blocks is going to have to be accessed with a waiting time every time. So let's query that petabyte data set, each block at a time in these trillion blocks. Let's start with block 1. block 2, block 3, block 4. And I continue like that. This is larger than the age of the universe. So you can imagine that it's completely unusable. This would be an example of a system in which you spend your whole time waiting. This is what I meant earlier when I said we don't want it to be latency bound. Well, if we have blocks that are kilobyte sized, we will be latency bound. There will be not much happening except waiting every time for a new block. For whom does that make sense? Right? Okay. So this is why this order of magnitude of a few hundred megabytes, 128 megabytes, is kind of a sweet spot between the two. It's neither too small nor too large. It's exactly the perfect size. It's small enough that you can spread it across machines, but it's also large enough that you don't spend your whole time waiting for accessing every blocks, right? So this is kind of the intuition. The other thing that I want to say is that you shouldn't be fixated on that exact number of 128 megabytes. It's good to know by heart, but it's the order of magnitude that is important. And in fact, this is why on the Google file system, it wasn't 128, it was 64 megabytes. In HDFS, it was doubles. Azure already went all the way to 4 gigabyte blocks. If you think of it, 4 gigabytes, it's still almost the same order of magnitude. It's not even a factor of 10, right? Well, it is, sorry, it is a factor of 10, but a factor of 10 is compared to trillions is nothing. The idea really here is that computers are evolving. The hard drives are getting a bit larger. The speed at which we can read keeps increasing. So over time, you would expect that the blocks are slowly going to be larger and larger, right? So this is why it's slowly evolving to maybe 1 gigabyte block, 4 gigabyte blocks. So this is the order of magnitude. But if I tell you 100 gigabyte blocks or a terabyte blocks, then no, now you have the intuition, no, this is a no-go, right? The right order of magnitude is somewhere around a gigabyte, 10 times less, 10 times more maybe, but this is the range, right? For whom does that make sense? Okay. Do we have a question on the chat? Mm-hmm. Mm-hmm. What is the relation? That is a great question. There is a relation with the defragmenting. So first, let me tell you about this. Who already used the defragmentation on your drive? Some of you, all right. Why do we do that? It's because these 4 kilobytes blocks here means that as soon as you have a file, even in the megabyte or gigabyte, it's going to be split into these blocks. The blocks on disk do not have to be contiguous, right? They are just blocks. You can store them anywhere. Just like in that case, the blocks are also not even on the same machine, right? You can put the blocks whenever you want. It's only contiguous within a block. Within a block, the bits are contiguous. Now, what happens is that when you have a disk on Windows or Mac or whatever, you use that disk. You keep writing and reading from the disk. And every time you delete files and write files again, at some point, the blocks are going to be all over the place, right? You might delete a file that frees up a few blocks. And then at some point, especially when the disks become full, you need to write a large files. It's no longer going to be possible to put the blocks together. So you're going to put a few blocks here, a few blocks there. And now what's going to happen has to do with latency. Because if you have a few blocks here and a few blocks there, then it means in order to read the entire file, you're going to have to wait. You're going to fetch a few blocks, then you have to wait to fetch some other blocks. Why? Because they are somewhere else. And every time it's somewhere else, you need the disk to rotate all the way to reach the reading head. That you're losing time whenever you do that. Now, the defragmentation, what it does is that it reorganizes the blocks on the drive and moves them around so that for each file, the blocks are again contiguous. This is what defragmentation does. It's just moving the blocks around to then put them together if they are in the same file. What do we gain from that? We gain that for the specific case of scanning through a file, you want to read the bits of a file in a sequential way, one after the other. If your disk has been defragmented, this is going to be very smooth. you might have latency initially for the first block, but since after that the blocks are now contiguous, you just read, and you don't even experience latency ever again. That's if you defragmented your disk. If you did not defragment your disk and the blocks are all over the place, every time you have a new block, you need to wait again. So who understands that defragmenting speeds up when you scan the data on your disk? Okay, very good. The notion of defragmenting is close to the notion of having a large block there. In fact, having a very large block could be seen as some sort of logical defragmentation, that we have this larger block, and we know they will never be split and distributed all over the place. So there is this link with defragmentation. Does that make sense? Did it answer your question? Yeah, awesome. That was a very good question. It's the first year that somebody makes a link with defragmentation, I think. Yes. Mm-hmm.
Is this problem solved by large cache?
Oh, yes, it is possible. So this is why actually maybe nowadays a lot of you don't even do defragmentation anymore. But this is just for illustration purposes, right? In the case of what we are doing now, we are not working at the scale of one machine, but the scale of the entire cluster. At the scale of one machine, it is true that now we have more modern ways of handling this, and the problem kind of went away, but not in a way that would work on the entire cluster. Okay? Should I move on? Yes, okay. All right, so now that I've told you about the logical model and the blocks and so on, and the size of the blocks, let's go to the architecture. So what is there inside of it? So a first aspect is we have thousands of machines. How do we connect them? So one way to connect machines, that's called the peer-to-peer network. That would be, for example, the blockchain, Bitcoin. Every computer can talk with every other computer. This is called the peer-to-peer network. Then there is another way of connecting the computers, and in fact, we like to use this way in the framework of big data. It is the idea that one of the computers coordinates everything, and the other computers are doing all the work, right? So there's many names that you will find in practice. I put a few examples there, but don't be too much surprised if you see all these lists. I probably will mostly say coordinator, worker, and so on and so on. All right? So this is the architecture we're going to have, like this. We just need to give them names. So every time we're going to have an architecture, we'll give them names. So the name we'll give to the coordinator node is name node in the context of HDFS, and the name that we'll give to the worker node is data node, name node, data node. Every week, there will be new names because we'll have new technologies that will keep using that same architecture. But this week, you have to learn by heart name node and data node. So we have one name node and we have plenty of data nodes, and they are connected in this way on the network. Now, you probably noticed that I put a few blocks on the data nodes, and indeed, this is where the blocks are. They are on the data nodes and not in the name node. Now, this is oversimplified. I put 3 blocks. It's in fact thousands of blocks on every machine, right? But I wasn't going to put thousands of blocks on my sites on every machine. So this is how it looks like. Now, so in the lecture hall, I need to make this, the toolbar disappear at the bottom. So let me see if I manage. Normally, that's the trick. Yes. I have no idea why I need to open and close the chat of Zoom to make this disappear, but it works. So we have a file, potentially 1 petabyte, and we want to store it on HDFS. What do we do? Well, first we cut it into blocks because this is what the model looks like. So we divide it into blocks or chunks or shards and so on, but blocks is the chunks would be for Google, blocks would be for HDFS. 128 megabytes, but again, be flexible, could be 1 gigabyte, could be 4 gigabytes, but in the case of HDFS, it's 128 megabytes. What do we do with these chunks? We distribute them all over the place. However, we also replicate them. Means that every one of these blocks is not just stored once, it's not just stored twice, it's stored 3 times. Every one of these blocks will be stored on 3 machines. So I took the example of this orange block right there. This orange block. There is a copy here, there is a copy here, and there is a copy here. These are called replicas. This is a block that has 1, 2, 3 replicas. The replicas have no particular order. There is no such thing as one replica that is more important than the others. These are just 3 replicas, okay, of the same block. Why is that good? Well, first, imagine this hard drive crashes, that's okay. We have 1 more copy here, 1 more copy there. We are safe. This is a way of ensuring fault tolerance to replicate. Second, it means that we can access for querying the data from multiple places, which is also some very good feature as we will see in MapReduce. So this is why we replicate. Does anybody know RAID? R-A-I-D? Okay, this is a way, it means redundant array of inexpensive disks, I think. This is a way at home you can buy, let's say, 4 hard drives, and then you connect them together in a way that you have some extra replications in there that make it more reliable and you can store more. Well, you don't need RAID if you use HDFS. So you don't need to worry about having any RAID system. The reason is that there's already replication in there. So having RAID on the servers would be totally useless. Right? So it's really completely orthogonal to that kind of system. But it's nevertheless interesting to see the relationship between this and RAID. Okay? Now, you can concurrently access this system. So imagine a company or Google or any large company, you have your cluster in the data center, and now all your employees can connect to the name node and to the data nodes and access the data, hundreds of people. It's all implemented in Java, right? But you can, of course, since there is a REST API, as soon as you have that is one, I don't know if I told you that, once you have a REST API, it's very easy to make it accessible through any programming language you want, because all programming languages understand REST. So it's implemented in Java. The most straightforward way is to access it programmatically with Java. But since there is a REST API, you could technically use any language to connect. All right, but now we need to look inside. I need to show you what there is inside of these machines. So I'll start with the name node, and then I'll go to the data node. So first, this is what there is in the name node. I'll pause on that slide and take the time to explain what is in there. I used to have an animation over several slides, but some of you told me they prefer to have less slides and more compressed. But then I'll just move on top of that and you'll understand. Okay, so 3 things. The first thing that you have on the name node is the file namespace. This here is a tree. It's the file hierarchy. These are your directory names and what directory is in what directory, what file is in what directory. So this is really your file hierarchy that is in there stored on the name node, right? It's stored on a single machine, this whole hierarchy, right? Access control, what does it mean? You know that on your file system, you might have users and groups that are allowed to read or write the data, and that says who is allowed to read and write the data. This is also the case here. You can also assign users and groups exactly as you do on a local file system. In fact, we will see, who know POSIX? POSIX is the standard for like what is used in Linux, Unix, and so on for the command line access to the file system, for example, and many other things. But this is here compatible with POSIX. A large part is in fact inspired from POSIX. So we have access control. I'm not focused too much on that, but it is possible to say who owns what data and who is allowed to read and write that data within the company. So that's the first thing. That's the information about the hierarchy. The second thing is, from the model, each file that you find here at the leaves is mapped to a list of blocks. For example, file 1 has the green block followed by the blue block, right? This is how it works. And then the same continues. Each file has a list of blocks. That's called the file to block mapping, right? These are the logical blocks before the replication. And finally, the third thing is the location of the blocks. For example, the green block is stored here and there, but what I want to say here is the name node knows that. The name node is aware of where each block is stored. So it keeps track of the block locations. Now, who agrees that if I have the file hierarchy and I know which file is mapped to what blocks and I know where each block is stored, that's enough information to rebuild the entire information? Who agrees with that? right? I have all I need. All I need, I look for a file with a path, then get to the file, list of blocks, and I know where to find the data, right? So this is everything we need, and this is all stored in the name node. So let's go to the data node in there. Well, this is in fact boring because what is there on the data node? What is there on the data node? Yes, the data, AKA the blocks. Yes, that's it. This is what we have on the data node, blocks, 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 blocks. So they are stored on the local disk. Of course, information is physical, right? They need to be stored somewhere. And in fact, the blocks of HDFS internally to the machine are actually files. This here, this block of HDFS is a local file. This block is another local file. This block is another local file. Each one of them is in fact a file that is stored on the local disk. But you really need to, it's data independence. If you are logged into that machine, and you can actually do it as an experiment, some people like to do that, you basically use SSH is a common way of connecting to a machine. So imagine you SSH yourself to that machine, and you look at the disk, the local disk of the machine. Then you will see these files. You will see actually the files that are your blocks in HDFS. But now, if you leave that machine, now you're outside, you're the user of HDFS, you couldn't care less that these are local files. You don't care. All you care about is these are blocks for your file system. So you really need to distinguish between the local file system of every data node, where each HDFS block is in fact a local file, and the global file system of HDFS, where you have the file namespace of the entire cluster. Do not confuse the two, right? There is the HDFS file system and the hidden local file systems that the users don't actually see, the users of HDFS. Is there a question? Yes, I'd say more about the protocol. So the name node knows which data nodes are available and knows which blocks are stored on which data nodes and how much space is used. Was it the question? Yeah. Are you happy with the answer? Yeah, all right. Okay. So blocks are stored on the local disk on every machine, but seen from outside, all we see is blocks. Okay, but at least it demystifies, right? Because there is no magic. In the end, each one of the data nodes is itself a computer with its own disk. Now, the nice thing is that since you have thousands of machines that each have their disk, each one of these machines can actually monitor the disk. And if the disk fails, they will know. And then the name node will know. And then it will be able to recover from that because it's replicated anyway. So we already know we have all the information. So we can detect the disk failure. And if a disk fails, or maybe even an entire computer fails, or even an entire rack of computer fails, we can recover from that. Now, I used colors for the blocks. I said the grid block, the blue block, and so on, right? But in fact, internally, we don't use colors. We use numbers. And more exactly, we use integers. But integers on 64 bits. It means that it's an integer between 0 and 16 quintillion. So you can see you can have a lot of blocks in there, right? So between 0 and 16 quintillions. So any integer basically gives you a block ID. This is how you identify a block. And these are unique in your cluster, all right? So if you go back to the slide where I told you a list of the list of blocks there, the file to block mappings, in fact, these are a list of integers, a list of the block IDs, okay? All right. Then another aspect that will be useful for MapReduce is that normally we access the blocks in their entirety. So most of the time we are going to read a whole block. But in some cases, as we will see in MapReduce, we might be interested in only reading a block partially, and that might happen. But do not abuse it, because if you think that this gives you random access because you can access any bits in any blocks, think again, because you will run into latency issues. So it doesn't mean you can have random access, but technically the API would allow you to read a block partially, right? It's an optimization really, because you could also read the entire block and then throw away what you don't need. Okay. So now that I introduced the name nodes and that I have introduced the data nodes, I'm going to explain how they talk with each other, right? So this is called the network protocol. This is how this whole thing is orchestrated and works nicely. Think of a symphony orchestra, and you have the violins and the brass and so on, and they just play together. So how does this work? I have oversimplified a few things here because in real life, there is a client, there is actually hundreds of clients connecting, there is a single name node, and there are thousands of data nodes, right? But I wasn't going to put 100 clients and 1,000 data nodes in there. So instead, I've put one client and 2 data nodes, but you have to imagine that there can be more. But if I look at a single client and 2 data nodes, this is what it looks like. There is communication between the client and the name node, between the name node and the data nodes, between the data nodes also, and between the client and the data nodes. Everything that is in a black arrow is called control. It means that there is no data in there. There is no data in here flowing. It's only talking with each other. The data, meaning the blocks, flow over these channels here, all over the data nodes to the clients. So this is the same thing, just with the name of the protocol. So this is called the client protocol. This is called the data node protocol. You'll see why I put a heart in there. It's not only that I love HDFS, there is a reason why I put a heart in there. Then there is the data transfer protocol that orchestrates the communication here, and this is called the replication pipeline, as we will shortly see. So let's start with the client protocol right there. So the client protocol is when a client, so the client means whoever wants to use HDFS from outside, the first point of contact is the name node, always, right? It's like your customer representative when you speak with a company. So this is the name node. And the client connects there for metadata operation. For example, you want to create a directory, you want to delete a directory, you want to initiate the creation of a file, you want to start reading a file and so on, always go to the name node. The name node will help you. It will give you the location of the data nodes you have to go to fetch the data. It will give you the block IDs that you need to get for a file and so on and so on. This is all doable with a Java API, okay? Second, so that was the client protocol. Second, the communication between the name node and the thousands of data nodes. So there are several things that happen in there. The first thing is the registration. You can have data nodes joining and leaving the cluster at any time, right? A computer can crash, then you lose a data node, or you can have installed a new computer to expand, and now you have a new one. So it can register to the name node. It connects to the name node saying, hello, I'm there, I'm a new data node, and now you can assign blocks to me, right? I'll be happy to store them. This is the registration. Once. Then there is the heartbeat. The heartbeat means that every couple of seconds, the data node connects to the name node just to give a sign of life. It's like, I'm here. I'm here. I'm here. Every couple of seconds. This is how the name node keeps track of which data nodes are still alive and which not. So this is called the heartbeat. Then every couple of hours, there is a block report. The block report means it's a full report with here are all the blocks I have and how much space I have available and so on, right? So a full report every couple of hours. And finally, we'll see when we write files, it can also confirm that it received a block successfully. The name node can give instructions to the data node. It can instruct a name node, it can instruct a data node to download and keep a copy of a new block, for example. It can give that kind of instructions. Now, what's very important is that the name node will never, ever connect to a data node to give instructions. It only gives instructions as an answer to a heartbeat. So if the name node wants anything from a data node, it just waits for a few seconds until there is a heartbeat. And then as an answer to that heartbeat, it will say, oh, by the way, I will need you to download that block from that other data node and keep a fresh copy of it, right? Because another one lost a block, and so you need a new copy. So this is what's important. It's always the data node that connects to the name node and not the other way around. In fact, it's one of the fundamental principles of computers talking with each other. There is always one that connects to the other. The one that connects is called the client, and the ones that answer is called the server. Okay, everything clear? The exact numbers, 3 seconds, 6 hours, are also orders of magnitude. It changes. It used to be 24 hours, and I think they diminished it to 6 hours. So if you read the papers, you will see that it's not 6 hours. It's the order of magnitudes that matters. In fact, you can also change these numbers if you are not happy with them. Okay. Yes. Mm-hmm. I'll talk about it. I have slides for the name node failure. I anticipated that question, but it's good that you ask. I'll just answer as soon as I reach the slides. Okay? So that's a good cliffhanger for the rest of the lecture. Okay, but if you ask these questions, it means you're understanding what I'm telling you. All right, so this is the data node protocol. Now we have this protocol between the data nodes. Now it's strange, why would the data node talk to each other? But in fact they do. Because when you create new files, you upload new blocks, right? You upload new data. Now, you could think, okay, if I replicate each block 3 times, why don't I just connect to the 3 machines? And for each one of the machines, I can send the block, right? But that would be inefficient. So instead of the client connecting to the 3 machines independently, the client is only going to connect to 1 machine, the first one. So it's connecting to that machine. And then the machines are going to just organize a pipeline among themselves. So the first machine will forward a copy of the block to a second one, which will itself forward it to the third one. Right? It's like you know, pre-internet, these phone trees that we had in a village. If you want to propagate news to everybody in the village, everybody calls somebody else and you let the news propagate, right? So this is how it works, but it's linear. It's not a tree, it's a linear because it's so few of them. So this is called the replication pipeline. For writing data, this is how the blocks are actually transferred. Much more efficient than the client connecting separately to each data node. Okay? Now, so I've covered now all the protocols, but a few more words on the metadata, what I call metadata functionality. This is between the client and the name node. What can you do? You can create a directory, you can delete a directory, you can write a new file, you can append to an existing file without creating a new one. You can read a file, you can delete a file, and so on and so on. For all of that, you need to connect to the name node first. Then you might need to also connect to data nodes. I have an animation for you that basically brings the whole thing into life of what I've been telling you. So the first animation is about reading a file, and then I'll have a second one about writing a file. So now you just sit back and watch what's going on. I simplified. There are obviously thousands of data nodes. At the bottom, I only put 3. On the right, you have the name node. But let's do it with 3. And I have a single client, but again, you can have hundreds of clients at the same time. So the client connects. We have a question on the chat.
Yeah. The confirmation of the success file transfer is only done when the replication is finished or when a single node has the whole file. When
it's finished. And I'll have it on the animation, on the second animation. Yeah. So when it's finished, but I'll come back to that. There is also a subtlety. Okay. So I'm a client. I want to read a file. What do I know? I connect to the name node. And I politely ask, now you have LLM, so you need to be polite, right? So you politely ask for the file. And then the name node is going to answer, yes, sure, that file exists. And here are the block IDs of that file. And here are the locations of these blocks. And by the way, you have the choice between these 3 data nodes for every block. And I even sorted them by distance for you so that you can connect to the nearest one first, right? All right, so now the client has all this information. Imagine that I'm not looking at MapReduce of Spark. I just want to read a file sequentially. It's the simplest way you can use it. So the client now is going to read sequentially that file. So it's going to connect to the data nodes and start streaming through the bits. Now, I want to explain a bit what's going on here, because there are multiple levels of abstractions. On a physical level, what the client should do is connect to a data node that has a copy of the first block, for example, this one, and then download the block. Then it needs block 2, So maybe this one has block 2, so it connects there and gets block 2. Then it needs block 3, and maybe block 3 is there, so it connects there and gets block 3. So on the physical level, you have to iterate connecting to the right data node and download the right block. But for convenience, if you are using Java or the Java API of HDFS, you don't need to worry about that because the programmers of HDFS were kind enough to program all of that. And they offer you what's called an input stream. It's one of the functionality in Java that does it for you. So basically what you get from the HDFS API is an input stream, and you just read the bits bit by bit, all the way, gigabytes of them. And the input stream will be intelligent enough to use the information provided by the name node and connect to the right places, right? So this is why in practice, if you read in Java, you will not even see the difference from a local file system because connecting to the data node is nicely encapsulated. Encapsulated is the word, encapsulated in the input stream. For whom does that make sense? Right. But technically, you're connecting to data nodes after data nodes to request block after block for a sequential read. Okay, now let's write a file, and I'll come to the acknowledgements. Oh, it's 10. So I'll explain how to write a file next week. I'll finish that animation, and then we'll wrap up on distributed file systems. So thank you very much for attending. You have a quiz that is going to be released today, tomorrow? Today at 12, a quiz on the cloud storage. Enjoy the exercises, and I'll see you next week at 8 a.m. Thank you very much.